Hey everyone! In today's video, we'll be talking about one of the more elegant tools in calculus, L'Hopital's rule, right? As you may or may not be able to see right in your face, right here. If you've ever tried to evaluate a limit and you ended up with an indeterminate form, like 0 over 0 or infinity over infinity, these are indeterminate forms. L'Hopital's rule gives us a way to handle these kinds of tricky situations. But more than that, it's also a window into how derivatives can help us understand how two functions behave near a point. Let's maybe build some intuition for what's happening and also go through a couple of examples. Let's take a look at sine of x over x for our first example. Looking at this graph, you can pretty reasonably conclude that sine of x over x approaches the value 1 as x approaches 0, right? But how do we determine this, or how do we approach this without a graph? As you go from left to right at the top, you can zoom in further and further and further until the graph essentially becomes a straight line, right? This ties in back with like linear approximation theorem that for very small distances from x is equal to 0, right, you can approximate the value of this point using the slope of the tangent line, right? So using that, this is a very terrible tangent line, but using that, you can realistically approximate this value to be 1, right? Keep in mind, this is not a straight line. This is not a straight line. This is a curve, right? As you've seen in the other diagrams over here, right? But you can approximate it for closer and closer and closer intervals. Now, let's try and break down sine of x over x into its numerator and denominator. Sine of x and x, right? From very small distances from x is equal to 0, we can approximate the change in sine of x by using the slope of the tangent line, which is 1 at this point, right? This happens to turn out to be x as well, right? But that was a coincidence. That was not intentional, right? The slope of this tangent line can be used to approximate values of cosine of x at different points, right? So maybe we define this, right? We're using the slope of the tangent line at x is equal to 0, and we're trying to approximate the value at, I don't know, x is equal to c over here, right? So our approximation would be here, whereas the actual value would be here, right? But for closer and closer and closer, like as we go this way, for closer and closer and closer values to x is equal to 0, the approximation is going to get better and better and better, right? Now, what about trying to find the value of x at x is equal to 0 itself? Well, what's stopping us from going backwards and using the derivative to approximate at x is equal to 0? Or in other words, what about an infinitely small change in x from x is equal to 0? We know that the derivative, we know that the derivative of cosine, not cosine, sine of x is equal to cosine of x, right? So some d sine of x change in height, right, would be cosine of x times dx, similar to the derivative of x. D dx of x will give us 1. So this ratio of sine of x over x can be approximated, or very loosely approximated, for values near x is equal to 0 as cosine of x dx over 1 times dx, right? And this in turn can be loosely approximated as cosine of x, right? And if we were to plug in cosine of x for x is equal to 0, right here, x is equal to 0, cosine of 0 is equal to 1, which corresponds pretty nicely to what we get up here. This is a very hand-wavy kind of intuition, but I mean, I hope it gives you the general idea. For more of a general form, let's say we wanted to evaluate this limit over here, right? If you plug in the value x is equal to a, and you get the indeterminate form either 0 over 0 or infinity over infinity, right? Then L'Hopital's rule states that this expression is equal to the limit as x approaches a of f prime of x over g prime of x. Okay? Right? This only applies if you have the indeterminate form infinity over infinity or 0 over 0, right? In only those two scenarios. However, if you see one of these indeterminate forms in this expression over here, you can apply L'Hopital's rule again. And as such, this expression would also be equivalent to the limit as x approaches a of f double prime of x and g over g double prime of x. Right? You could keep applying this rule over and over and over again until you get a form that's not either infinity over infinity or 0 over 0. Right? Let's see a couple of examples now. Let's try an example with a rational function over here. All right, if we were to evaluate this at x is equal to 2, we would get 2 squared minus 4, which you probably already know is 0. 2 squared minus 3 times 2 plus 2 in the denominator, which is also equal to 0, so you would get an expression of 0 over 0, which means we can apply L'Hopital's rule. Now, of course, you could probably factor this out into x minus 2, x plus 2, and factor this into x minus 2, x minus 1, and then factor out or cancel out the extra factor, right? But we are not going to do that because this is a video demonstrating L'Hopital's rule, right? So the limit as x approaches 2 is equal to the derivative of this expression over the derivative of this expression, which is 2x over 2x minus 3. Right? And if we were to plug in the value 2 here, we would get 2 times 2 over 2 times 2 minus 3, which is equal to 4 over 4 minus 3, which is equal to 4. All right, let's do something a little bit more hands-on this time. Let's say we have the limit as x approaches 0 of x minus sine x over x cubed, right? If we were to plug in 0, we would get 0 here, 0 here, sine of 0 is 0, right? And 0 here, so our 0 over 0 gives us permission to use L'Hopital's rule, right? This is also equal to the limit as x approaches 0 of 1 minus cosine of x over 3x squared. Derivative of sine is cosine, right? Let's say we plug in 0 again, right? We would get 1 minus 1 over 0, right? So our 0 over 0 indeterminate form still exists. So let's apply L'Hopital's rule again. So this would be equal to the limit as x approaches 0 of sine of x. This constant disappears, right? And this negative sign flips to a positive because the derivative of cosine of x is equal to negative sine of x, right? Over 6x, right? And now from this, you can determine a standard limit here, sine of x over x, which you probably already know to be 1. So we can factor out this 1 over 6 in the bottom. So 1 over 6, limit as x approaches 0 of sine of x over x, which is equal to 1 over 6. And there you go.